In this video we look at the work on hyperbolic functions for Unit 4 of the WJEC Further Mathematics specification. The specification states that we need to understand and be able to use the definitions of sin x, cos x and tanh x, including their domains and their ranges, and be able to sketch their graphs. We need to be able to differentiate and integrate hyperbolic functions. We need to be aware of the inverse hyperbolic functions and the logarithmic forms for these inverse hyperbolic functions. And we need to be able to use hyperbolic functions to integrate further functions of the form 1 over root x squared plus a squared and 1 over root x squared minus a squared, and similar types of functions. So in terms of key facts, we have the definitions of the hyperbolic functions, and you do need to be able to sketch the basic 3 hyperbolic functions. There are 3 more hyperbolic functions which are not explicitly mentioned in the specification, but certainly if you're going ahead and doing step papers or anything like that, it's well worth your while knowing the definitions of those as well. The hyperbolic functions have lots of properties that are very similar but slightly different to the ones for trigonometric functions. Many of these are in the formula booklet. The ones that aren't in the formula booklet can be derived relatively quickly. So that last lot there are the hyperbolic function equivalents of the compound angle formulae. Ones that are particularly important are the ones for sin 2a, cos 2a and tanh 2a. Those fortunately are in the formula booklet. It really is important you know what is and what isn't in the formula booklet. The differentiation and integration results for the basic hyperbolic functions are relatively straightforward. The definitions of the inverse hyperbolic functions and their logarithmic formats are given in the formula booklet. You might be asked to derive any of these logarithmic formats for the inverse hyperbolic functions in the course of a question. It is quite important to remember that if you're solving the equation cos x equals p, where p is a number greater than or equal to 1, then it has got 2 solutions, namely x equals cos to the minus 1 of p and x equals minus cos to the minus 1 of p. The differentiation results for inverse hyperbolic functions need to be known, and you need to know how to derive these results as well. And these differentiation results rapidly give some important results about integration, which are also in the formula booklet. We need to be able to handle integrals of these 3 types. And one strategy for doing these would be first of all to complete the square of the quadratic expression, and then having completed the square, make a substitution. Having done that, you should end up with, if the original integral was 1 over ax squared plus bx plus c, you should end up with something of the form 1 over u squared plus alpha squared, or 1 over u squared minus alpha squared, or 1 over alpha squared minus u squared. Each of those are standard integrals given in the formula booklet. Similarly, if the original integral was 1 over root of ax squared plus bx plus c, then by the time you've done the substitution, you'll have ended up with 1 over root of u squared plus a squared, or 1 over root of u squared minus alpha squared, or 1 over root of alpha squared minus u squared. And each of those are standard integrals. The final case is slightly more awkward. If the integral was root of ax squared plus bx plus c, once we've completed the square and made our little substitution, we'll either end up with root of u squared plus alpha squared to be integrated, in which case we use the substitution u equals alpha sine theta, or we end up with root of u squared minus alpha squared, in which case we use the substitution u equals alpha cos theta, or we end up with root of alpha squared minus u squared, where we need to use the substitution u equals alpha sine theta. Okay, so at this stage we need to start having a look at some examples. So in the first example, we need to find the exact solutions of the equation cos 2 theta equals 6 sine theta minus 3. So we've got cos 2 theta equals 6 sine theta minus 3. We're told in the formula booklet that cos 2a is the same thing as cos squared a plus sine squared a. So we can instantly rewrite the equation as cos squared theta plus sine squared theta equals 6 sine theta minus 3. We also know that cos squared x minus sine squared x is always equal to 1. So cos squared x is the same thing as 1 plus sine squared x. So our equation again can be rewritten now as cos squared theta being replaced by 1 plus sine squared theta. So the equation is now 1 plus sine squared theta plus sine squared theta equals 6 sine theta take away 3. Tidy that up, we can create a quadratic equation in sine theta. So we've got 2 sine squared theta minus 6 sine theta plus 4 equals 0. Divide by 2, sine squared theta minus 3 sine theta plus 2 equals 0. So that's sine theta take away 1 times sine theta take away 2 equals 0. So we've got sine theta must equal 1 or 2. So theta must be sine to the minus 1 of 1 or sine to the minus 1 of 2. We know that sine to the minus 1 of x is the natural logarithm of x plus the root of x squared plus 1. So we can now say that theta is sine to the minus 1 of 1, which is the natural logarithm of 1 plus root 2, or theta is sine to the minus 1 of 2, which is the same thing as the natural logarithm of 2 plus root 5. So we've now got our two solutions to the equation in the required format. So moving on to a second example, we have to prove that the integral between 0 and 1 of x sine x is 1 over e. The way to progress on this question is to try a integration by parts. It shouldn't be surprising because what we've got here is a product of a polynomial with a hyperbolic function, and often when we have a product of two different types of function to integrate, integration by parts is a sensible way to proceed. So using integration by parts, we can say that the integral between 0 and 1 of x sine x, now I'm going to integrate the cos x to begin with, the sine x to begin with, to obtain cos x, and then differentiate the x term. So we've got the integral of x sin x dx between 0 and 1, leaving the x alone. Integrating the sin x, I get cos x. And then I must subtract the integral of the x differentiated, which is 1, times the result of the integration that I've already done, which was the cos x. That final integral is the integral of 1 times cos x, and the integral of cos x is sin x. So I've got x cos x, take away sin x. Putting the limits in, well, for the first term we're going to get 1 times cos 1, take away 0 times cos 0, which just gives me 1 cos 1. And for the second term in the expression, we've got sin 1 take away sin 0. Sin of 0 is 0, so we're left with simply cos 1 take away sin 1. Cos 1 is e to the 1 plus e to the minus 1 over 2. Sin 1 is e to the 1 take away e to the minus 1 over 2. If we simplify that, we simply end up with e to the minus 1, which is precisely the same thing as 1 over e. In our next example, we have to show that the function f, which is defined on the non-negative numbers by f of x equals sin 2x minus 14 sin x plus 8x, we have to obtain the derivative of f. We have to show that f only has one stationary point and find its x-coordinate, and we have to determine whether that stationary point is a maximum or a minimum point by obtaining f double dash x, the second derivative of f. So we've got f of x is sin 2x minus 14 sin x plus 8x. The derivative of sin 2x is 2 cos 2x. The derivative of sin x is just cos x, and the derivative of x is just 1. So to differentiate f of x, we can just write down f dash x is 2 cos 2x, take away 14 cos x plus 8. Now that isn't quite the expression they were asking us to get. The expression they were asking us to get was one where we had f dash x as a quadratic in cos x. So we're going to need to use some of the results in the formula booklet again. We're told that cos 2x is the same thing as cos squared x plus sin squared x. So we can replace the cos 2x by cos squared x plus sin squared x. And then we also know that cos squared x minus sin squared x is always equal to 1. So sin squared x is the same thing as cos squared x take away 1. So we've got two lots of cos squared x plus cos squared x take away 1 minus 14 cos x plus 8 is our expression now for f dash x. And if we simplify that, we end up with 4 cos squared x minus 14 cos x plus 6. And take out the common factor of 2, we've got two lots of 2 cos squared x minus 7 cos x plus 3, which is the answer we were chasing after for part A. For part B, we've got to show that there's only one stationary point on the graph of f. So if we've got a stationary point, we must have the value of f dash x to be equal to 0. So for a stationary point, we must have 2 cos squared x minus 7 cos x plus 3 equals 0. Well, we've got a quadratic equation there in cos x. That quadratic equation will factorise, and that will give us 2 cos x take away 1 times by cos x take away 3 equals 0. which tells me that either cosh x is a half or cosh x equals 3. Now if you think about the cosh function and can picture its graph, you'll remember that the value of cosh x is always at least 1. So the fact that we know that cosh x is always at least 1 tells me that cosh x equals a half is impossible. If you didn't remember that and you tried to find inverse cosh of a half, you'd find your calculator would give you an error message. So we know that cosh x must be equal to 3, and that means that x is plus or minus cosh to the minus 1 of 3, which is plus or minus 1.76. However, at this stage we need to recall that the function f is only defined for non-negative numbers, so we've got to reject the negative value at this point. So we've now got that x must be 1.76. So we've shown that f has only got one stationary point, and that stationary point is x equals 1.76. Now at this stage we need to do another differentiation. We had earlier on that f dash x is 2 cosh 2x minus 14 cosh x plus 8. This is the easier one to differentiate a second time, so we'll use this one. So the second derivative of cosh 2x is 2 sine 2x, and the derivative of cosh x is just sine x. So we've got derivative of 2 cosh 2x is 4 sine 2x, and the derivative of 14 cosh x is 14 sine x. If I take x equals cosh to the minus 1 of 3, then the value of f double dash x is 28.28, which is a positive number. So f dash x is 0 and f double dash x is a positive number, then we know that the stationary point is a minimum. Moving on to our final example, we have a couple of integrals to do. The first one we have to do is to find the exact value of the integral between 0 and 4 of 1 over root of 4 plus x squared. Well, in this case we have a standard integral which is given in the formula booklet, so we can make straight use of that. We're given in the formula booklet that 1 over root of a squared plus x squared integrates to sine to the minus 1 of x over a. In this case a squared is 4, so a is 2, so we've got the integral becomes sine to the minus 1 of x over 2. Put the limits in. That means I've got sine to the minus 1 of 2, take away sine to the minus 1 of 0. Sine to the minus 1 of 0 is 0. And we've also got the fact that sine to the minus 1 of x is the natural logarithm of x plus root of x squared plus 1. So sine to the minus 1 of 2 is the natural logarithm of 2 plus root 5. As we've already commented, sine to the minus 1 of 0 you may know is 0. If not, use the formula again. We've got ln natural logarithm of 0 plus square root of 0 squared plus 1, which becomes the natural logarithm of 1, and the natural logarithm of 1 is 0. So our answer for this is simply natural logarithm of 2 plus root 5. The second integral that we've got to calculate is the integral between 1 and 2 of the square root of x squared minus 2x plus 2. And we are allowed in this case to give the answer correct to 3 decimal places. Well, our strategy for examples like this was to begin by completing the square. So x squared minus 2x plus 2 is the same thing as x minus 1 squared plus 1. So we can now rewrite our integral as the integral between 1 and 2 of the root of x minus 1 squared, add 1. At this stage we make the substitution u equals x minus 1. If you have u equals x minus 1, then du by dx is 1, so in other words du and dx are the same thing. And when x is 1, u is 0, and when x is 2, u is 1. So our integral now can be written as the integral between 0 and 1 of the root of u squared plus 1. So moving to a new page, we've got the original integral now we know is the integral between 0 and 1 of the root of u squared plus 1 du. Now we're going to have to make a substitution on this one, and the substitution that's going to be useful here is u equals sine theta, because if I make the substitution u equals sine theta, u squared plus 1 is sine squared theta plus 1, which is cos squared theta. So the square root of cos squared theta is just cos theta. So that will instantly remove the whole of that rather awkward square root term. So we're going to make the substitution u equals sine theta, or equivalently theta equals sine to the minus 1 of u. So du by d theta is cos theta, which means that du is the same thing as cos theta d theta. When u equals 0, we've got theta is sine to the minus 1 of 0, which is 0, and when u is 1, we've got theta is sine to the minus 1 of 1. So making the substitution, we've now got the integral between 0 and sine to the minus 1 of 1 of the square root of sine squared theta plus 1 times by cos theta d theta. We know that root of sine squared theta plus 1 is the same thing as cos theta. So our integral simplifies to the integral between 0 and sine to the minus 1 of 1 of cos squared theta. There are several ways of handling the integral of cos squared theta. One way is simply to revert to the definition of cos theta as being e to the theta plus e to the minus theta over 2. So we've got to square that, and if we square that we end up with e to the 2 theta plus 2 lots of e to the theta times e to the minus theta, which just gives me 2, plus then e to the minus 2 theta all over 4. So I can rewrite the integral again, this time as the integral between 0 and sine to the minus 1 of 1 of a quarter e to the 2 theta plus a half plus a quarter e to the minus 2 theta, which is now a straightforward integration. So I've got 1/8 e to the 2 theta plus a half theta plus minus an eighth e to the minus 2 theta. If I insert now the limits and do all of this on my calculator, I'm going to end up with a final answer of 1.148.